Thanks everyone for coming. I'm sure I'll adapt eventually. So, boy, that's a pretty exciting title, right? The apocalypse. There's going to be all sorts of apocalyptic destruction described here. But seriously, though, this is what a lot of people got into quantum computing for in the first place, right? Let's face it, this industry wouldn't even exist, I don't think, without Peter Shor's algorithm. It threw a whole bunch of fear and money into the industry and just kept it steamrolling ahead. And sure, eventually, we started getting to awesome use cases, but it's that thing that's always been in the back of our minds that we've been worrying about. And, oh, we got a problem here. I don't think this is working. Is this the right one? Oh, okay. Yeah, my art was better. Yeah, I basically asked an AI, you know, what do you think the quantum apocalypse looks like? And it came up with that. I mean, that's pretty damn scary, right? That's pretty awful. I added the NIST. They're not that great with letters yet, no matter what they say. They still mess it up. I tried, though, in NIST, by the way, and then I got like N and T or N and S, but never all 4 letters. It's just 4 letters, people. It's not that much. So, okay. I do quantum computing service at Protiviti. Basically, I help companies with use cases, and I also help companies with their post-quantum cryptography, you know, getting ready for this apocalypse that's coming. I also host the Post-Quantum World podcast. I'm always looking for guests, so if you're doing something in industry, that's great. And I'm assuming I'm not controlling the slides, right? That's not okay. So the apocalypse. Like I said, this is something we've been worrying about from the beginning. And whenever we would talk about it, what would we talk about? We would think about qubit numbers, right? That was all it was. Everyone just thought of, you know, you get to X number of qubits, here's the apocalypse. It kind of became a simple thing like that. But today we're going to talk about the fact that that's just not true. That's not when the apocalypse begins. There are a lot of variables that could change the timeline. Interconnect, something that was kind of hinted at on this stage. This idea of making quantum computers work together as one, that could certainly accelerate the timeline. You know, instead of needing, let's say, 4,000 logical qubits in one machine, you just need 4 1,000 qubit machines connected together. That's great. All that can accelerate. But if you're involved in information security, when does the actual apocalypse work begin for you? And thanks to NIST, that's just a few months away. So 2024 is really the beginning of the end. This is where everything is going to change, and you really don't have any choice but to become part of it. So that's kind of what this talk is going to be about and what's causing that. So I guess next slide. That's not really doing anything. Yeah. So it all started with the NSM-10 memorandum that the White House put out in May 2022. And this was kind of like a combination of future thinking and what we should be doing now, and sort of like bragging about America, all rolled up into one. But this is a pretty great document to read, because for the first time, we have telegraphing of what's going to happen all across the industry, not just federal agencies. So I have to point out that this is not a talk about just like federal. In fact, it's a talk about how anything for federal agencies is going to roll over into the private sector and affect everybody. So the first few sections talk about how the US has to be first, training's important, funding, all that great stuff. But then it starts to, oh, we got one that works. Okay, cool, thank you. But then it starts to delve into actual meat and things that will affect the security issues. So in May 2022, Section 3 started talking about NIST finalists being on the horizon. And it said that by 2024, we're going to have them. And all signs point to yes. It's been progressing since then. And it was funny, I was speaking about NSM-10 in New York City a couple months ago. And after my talk was done, a guy came up to me, introduced himself. And I was like, wait, don't I know? And he was like, oh yeah, I wrote NSM-10. So that was kind of a funny moment, but anyway. So I got to meet the author. That was a fun day. His name's Jonah. So we were talking a little bit about this. In July 2022, NIST identified 4 candidate algorithms for standardization. They stayed the same, and then 3 out of 4 of them this last July got draft standards, goes Crystal's Kyber, and then the other 3 have to do with digital signatures, not actually sending the data. What's interesting is, you notice July. In my head, I'm thinking we're going to have the finalists in July. I mean, it just seems to be the trend, but we'll see. Maybe it'll come sooner. But that's my prediction. And there's still other chems under consideration: Byte, Classic McLeese, HQC, and Psych. Psych, one implementation was attacked by a laptop. That's a side channel attack. But notice Crystal's Kyber, which is currently one of the final standards, generated a lot of buzz recently. Some of you might have seen the news, but this thing is not working well. Okay. So basically, there was news that Crystal's Kyber was hacked. And when you're trying to replace vulnerable cryptography with something new, the last thing you want to hear is that the new cryptography got hacked. Cryptography is really, really hard, right? But what happened here was Crystal's Kyber was a proof of concept bit of C code to show how a new algorithm could be implemented, okay? And to make sure that it's post-quantum safe. It was not a production-ready piece of software ready to roll out to systems. So this team that did this testing built it into a production bit of code. And they added something called higher order implementations of masking. So that's, to simplify it, you basically take a secret and you break it up into 5 or 6 pieces and you distribute it, and it makes it harder to attack. So what they did was they built their own higher order implementation, and then they used machine learning to listen to the processor and how it was handling electrical signals in a side channel attack. And AI was able to, 99% of the time, piece together all the higher implementations and reveal the key. So that's what they called hacking Crystal's Kyber. But the number one thing to remember is they wrote code and then said they hacked it. That's kind of a no-no. If you stood on the DEF CON stage and said, I'm a hacker, I wrote a program and hacked it, you'd kind of get laughed off the stage. You can't write it and then claim to have hacked it, right? So it is useful. It shows us things not to do, but Crystal's Kyber is still valid and is still on track to be a finalist. So I just wanted to point that out. Okay, so another action that came out of NSM 10 was this idea of annual crypto inventories, and this is something that everyone's gonna have to start doing soon. The first to take the reins and do one of these is the OPM. Now, some of you might remember the OPM was victim to a pretty big attack a few years ago. And there's nothing like getting a whipping that'll make you, like, you know, do your hygiene better, right? So after OPM was attacked, they were like, hey, we're gonna be first on this. So they issued their own memorandum, and in it they list like all steps to take, how to do post-quantum cryptographic assessments, which is really, really useful. They published this chart in there. This isn't groundbreaking stuff. It's just that I just wanted to show a sample of what they put out to their folks to show them what to start looking for. And when people ask me, you know, if you're doing an inventory, which systems are vulnerable to, you know, quantum attack? And the answer is usually all of them. But yeah, so it's like the easiest inventory you'll ever do. But they did actually establish this and start putting it forward. This very month, the NSM 10 calls for NSS systems, so national security systems, to start adding extra cryptography protections. And what's interesting about this is in NSM 10 it says you can't buy any post-quantum solutions before the finalists in 2024. So they don't want to handle like anything like that. They just want it to be finalized first and then recommend buying. Federal agencies can buy things to test them. They just can't roll them into production. So it makes sense. But this month, HAIPE, it sounds like a lot of hype to me. Just kidding, anyway, it's not spelled. But yeah, so what it does is it basically lets you have pre-shared keys at endpoints, which is a good idea. It's out of channel. It's sort of like protected automatically. And Dennis you might have heard he mentioned something they do at Crypt. And I could see this rolling out into more of the private sector too, in that you have these keys provided to endpoints by some other means. In the case of Crypt, they use actual quantum devices to generate random numbers. And then that way they can have really secure keys sent by the cloud to endpoints. And then they could communicate out of band without any chance of anyone eavesdropping or picking up any key data or anything like that. And those keys change really, really, rapidly. So this is like one extra last little layer that's being done before we have our new replacements. So I wanted to mention that because that's due by the end of this month for national security systems. Now, what does all this mean for the rest of the world and the coming apocalypse? So 2024, like we said, there's going to be new standards issued. Once they're issued, a bunch of things kick off. Something happens 90 days later, symbolized by that little padlock there. We're going to zoom in on that in a moment. I'm not going to say what that is just yet. Within 1 year, so by 2025, you have to have a plan for migration. not an inventory. So this is how we're going to migrate to post-quantum cryptography. That's due if you're a federal agency. So keep in mind, like anything you see from now on when I'm talking, federal agencies have to do, but private sector regulators, they're going to start to copy this. Do you really think private sector regulators are going to invest like $100 million to come up with to the solutions that the government came up with already? Absolutely not. So for the first time, we have a true telegraphing of what's coming. If you read NSM 10, it's practically like reading a manual for what your own sectors are going to be asking of you in the future. So within a year, you can expect to have to start having a plan for migration. They're saying that by 2035, all migration needs to be done, for better or worse. Now, I don't know if I really agree that it's going to be till 2035 before a quantum computer is powerful enough to crack cryptography. I say that for a few reasons. One is, I mean, we're always being surprised in this field, right? And there are those wildcard technologies like interconnect. We just don't know how that's going to affect us. We might not have, it might not be that hard to chain together a few quantum computers and get enough qubits. You only need around 4,000 to start doing interesting work. 4,000 error-corrected qubits, of course. But we're rapidly approaching it. I mean, you know, IBM's going to have probably 1 million qubits by 2030. And then it's just down to error-correcting ratios. You know, how many of them will be good qubits? You know, will it really be 1,000 to 1? Will it be 100 to 1? If it's less than 100 to 1, then all of a sudden you're starting to have some danger zones. But that's their target. That's what they're setting. But it might not even matter. So back to what I said earlier, everyone used to worry about qubit counts and all that. That's not really what the problem here is. Let's zoom into that padlock. This is the problem that everyone is forgetting and no one is talking about. 90 days after NIST publishes their standards, the first timeline for deprecation of ciphers is due, and this is going to be revised every year. So if anyone here has ever worked with cryptography, you know that once a cipher is deprecated, it's done. You know, I don't care if you're a quantum denier, if someone in your organization believes quantum is a fairy tale and we're never going to have machines of more than a handful of qubits or we're never going to exit the NIST era, doesn't matter. Once a cipher is deprecated, it's everybody's problem. You will start failing audits. You won't be compliant. Regulatory bodies are going to come down on you hard. It's going to show up on every single type of pen test or audit, anything you do throughout the year. So this is the real make or break moment to worry about. It's that deprecation of ciphers. And when there's deprecation, there has to be then a timeline for remediation, and that becomes everybody's problem. So that's why in 2024, 100%, this is going to be something that everyone has to start dealing with because we're going to see those timelines for deprecation. So it's nice and refreshing, right? We now know when the end begins. You know, you don't have to like wonder and fantasize about what you're going to have to face in the future. It's now. You know, we're basically here. So leading up to that, I mean, there's a few things you could do. There are other considerations to make, like the harvest now, decrypt later thing. That's another reason why you should have already started this. You know, like you heard in the last talk. Moscow's theorem is really simple. You know, X is the amount of time that a secret needs to remain a secret. Y is the number of years that it takes your organization to migrate to a new cryptography, which is usually pretty high, big number. And you have to ask yourself, if you add those two numbers together, is it going to be bigger than the number of years, Z, that we expect a quantum computer to be powerful enough to crack cryptography? So if you're in healthcare, you've already blown this out of the water because the lifetime of a secret in healthcare is, no surprise, a lifetime. So, you know, it's already too late. If it's a credit card number, yeah, 5 years, whatever, who cares? So maybe not that. But depending on where you are, Moscow's theorem helps you figure out if you're already late to the game. Just wanted to point that out. There are some implementations that are helping people stay safe now. On the cloud, ironically, for the first time, it's the easiest time to sell the cloud on people because people used to be afraid of the cloud. If you're in the cloud, AWS, for example, is already using hybrid post-quantum where they're wrapping traditional cryptography with post-quantum finalists. But for all other intents and purposes, you have to start planning your migration. And it's basically these 4 major steps. We're not going to dig that deeply into them. We're kind of running out of time. But basically, it's about understanding your data, understanding your cryptography, how it flows, what ciphers are in use, what third parties do you have. That's the thing everyone forgets about. third parties might not have a path towards post-quantum cryptography. So you're going to have a real rough year if you're working with third parties that are just like, I don't know. Abstracting it out is another big one. If you're writing code, you can't be hard coding cryptography in. The time is now to stop doing that. You want to have a more modular approach. And then ultimately, it's all about becoming crypto agile and able to just implement post-quantum cryptography going forward. So yeah, you've got like a few weeks. Get started. So that. So I don't know. I mean, we're pretty much right on time. I don't know if we can take maybe one question. Okay.
For me, this is the first time witnessing this changeover. Can you reflect historically on how RSA 2048 came to be and what that all looked like? You know, the current encryption we're using, right? What was that transition?
Yeah. So the last example I could think of would be when we tried to do elliptic curve, and anyone who got involved in that project found it to be like a 10-year project. You know, it was a nightmare. So I'm anticipating the Moskow's theorem math to be really, really large, you know, like some large variables. Luckily, that said, we did learn a few things about agility since then. Just the fact that the term crypto agility exists means we learned a few things about agility since then. And I do believe that if folks start getting ready, there are products that you introduce to your life cycle anyway, right? You buy a key management solution. There's certain things you do. And I just want to make sure that everyone realizes they shouldn't be buying anything that doesn't have that post-quantum path built in. And this applies to other areas your organization might not think about. Like if you're doing anything in DLT, like let's say you still think that blockchain is useful. If you're doing it in that space, you would want to build on one of the platforms that has like, you know, so-called switches in place for coding forward into post-quantum. That's like another example. So the things we buy, the things we implement, the things we roll out, fortunately, some of them already are on this path. Mm-hmm. Mm-hmm. Yeah, that's why if it were up to me, I would push for hybrid. So like, I really like what I'm seeing in the hybrid space because think about it. You're taking a post-quantum wrapper and you're having ECDSA inside, let's say. And then, you know, a quantum computer will be confused by that wrapper. And let's say there is some side channel attack or whatever. The old tried and true is still inside. So I'm a big fan of that, but we'll see. We'll see where that goes.
All right, maybe really short question.
So I'm a fan of PQC, especially when it's used with these entanglement-based quantum networks. Do you think, though, that PQC is math-based? Eventually, do you think it's going to get slaughtered by physics? I mean, you can't really need physics to beat physics versus these math-based algorithms. What are your thoughts on that?
Yeah, so the beauty of math-based is our entire infrastructure is math-based, right? Like right now, you have TLS, you know? So it is much easier to just go to TLS 1.3 with hybrid post-quantum cryptography, whatever. Like Google Chrome already supports it. You know, it's easier to just roll out the infrastructure we have. But physics-based has its own limitations, right? QKD requires end-to-end, you know, like boxes, sending photons, that kind of thing. I used to work on QKD security years ago. So it's going to be hard to replace that. But so QKD will be a nice add-on to those like really high-profile targets, you know, one federal building to another or a bank to a bank, whatever. So it still has its place, and of course it's going to be important to the quantum internet's future. It's just right now we have to realize, you know, we have cell phones, you know what I mean? And no one wants to be trying to catch photons from a satellite. We all saw how great that worked out with the even just emergency call plans of Apple and Google. So yeah, those are the limitations of physics. It's hard to implement to the world we live in right now.